Hello, I welcome you all. The problem reads that the force exerted by the motor on the cable is shown in the graph. Determine the velocity over the 200 pounds crate when t is equal to 2.5 seconds. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Hibbeler. So we have a force being exerted by a motor on the cable and it is shown in the graph, and it's a function of time and it's a linear function. And we have been asked to determine the velocity of the crate when t is equal to 2.5 seconds. So let's write this equation as a function of time. So we can write this, okay, f itself is just equal to mt plus c. Remember this is from y is equal to mx plus c. Okay, our y is f and our t is x. Okay, so now, and then m is the gradient. Let's find m, which is the gradient, which is the change in f divided by the change in time. So this is just a 250 minus 0 divided by 2.5 minus 0, and this just gives us, what does this one give us? 1000. 250 divided by 2.5, 100, right? Okay, and therefore, and then we also know that if we are to replace, we know that also from this equation c is equal to 0. Okay, therefore f itself, okay, which is a function of time, is just going to be equal to 100 t, right? That's a function of our force. Okay, that's 100 t. Okay, so f is equal to 100 t. So now let's write down the free body diagram in this particular system. Let's magnify it a little bit, and once we do so, then we are going to have something like this. Okay, magnify it a little bit. So let's section there, we section there, so that we check the tension in the cable. So we have tension there like so, going over the pulley, and we are assuming there is no friction between the cable and the pulley. Okay, so we have a system like this, and this is F, okay, which is F there, and this is the same F there, and this is F there, like so. Right, and we do have some weight there for our box, and this weight is just W, which is equal to mg. So we want to apply the equation of motion, and we are going to say going up, okay, going up is our kinetic diagram, like so. All right, this is our MA. Okay, so let's write down our equation. So we'll say summation of forces in the y going up in our reference positive, this is equal to MAY. So we have F minus W. F minus W is equal to MA. We know what F is, that's just 100 T, minus W, we know what it is, it's just 200, and our M is just 200, it is in pound, divided by the acceleration due to gravity in feet per second squared, 32.2 times A. Okay, let me just create a boundary there like so. Right, so what do we have here? Let's write A in terms of T. A is just going to be equal to 200 into T, or 100 divided by 200. I mean, by there is also 32, sorry. So we have 100 divided by 200, which is also divided by 32.2. Okay, so this becomes a 16.1 t, and then minus, this is 200 divided by 200 divided by 32.2. So this is just 32.2. So this is the acceleration in terms of t. The question is to find the velocity. We know that acceleration is just a dv dt, right? And our dv is just equal to a dt. And once we integrate this velocity from 0 to v, then from t naught to t final. But we have to calculate the t naught, right? We've seen this, it's not from 0. We need to find the point when this system is in equilibrium, right? Okay, so let's find t naught when the system is in static equilibrium before it begins to move, right? Before it begins to move. So we'll say summation, we need that t as one of our boundaries. So summation of forces in the y is going to be equal to 0, going up being our reference. So we have F minus W equal to 0, and therefore here we have what do we have? 100t minus 200 equal to 0, and our t, which is equal to our t naught, is equal to 2 seconds. So this is the time when our v naught is equal to 0. So when v naught is equal to 0, v naught is equal to 0 at t naught equal to 2 seconds. Alright, and we want to use this in our kinematic equation to compute the final velocity. Okay, so we know from our kinematics that our acceleration is equal to dv dt, and making dv subject of formula, this just becomes dv equal to a dt. Then we integrate this, okay, from 0 to v, and then there from t naught to t. So we have v is equal to integral, our t naught, we calculated it as 2, and our t final is given here, is equal to 2.5. And our acceleration, we just from calculated it is 16.1 t minus 32.2, right, dt. And if we are to integrate this just becomes integral from 2, let's integrate it. This just becomes 16.1 t squared divided by 2 minus 32.2 t. Okay, and we are evaluating the whole lot of this. We are evaluating this from 2 to 2.5, and therefore our v is just going to be equal to, we just create a boundary there like so. Our v is just going to be equal to 16.1 by 2 squared divided by 2 minus 32.2 by 2.5. 16.1 by 2.5 squared divided by 2 minus 32.2 by 2.5. and then minus again 16.1 by 2 squared divided by 2, and then the other part there is adding 32 by 2. So we have a 2.0125. So therefore our V is just going to be equal to 2.01 feet per second, right? Feet per second. I think this is about it. We have found the velocity, and this velocity of course is going up. I just need to show also here. I didn't show in the other video. This is going up. So this is our velocity for the crate. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screen.